All right, welcome. This is Ralston Valley High School Chemistry's AP Chemistry Lecture Series. We're looking now at Chapter 15, in which we'll discuss indicators. Let's go ahead and move forward. All right, to begin our discussion of indicators, recognize that you have seen the use of acid-base indicators in your previous experiment during your first year of chemistry, in which we did an acid-base titration. In particular, during that titration, we used the indicator phenolphthalein. Indicators like phenolphthalein are generally composed of a weak acid which is present in solution. And the key idea about how that indicator functions is that the weak acid itself and the conjugate base of that weak acid should have different colors in a solution, such that as the dominant species present in the solution changes from acid to base, that is the weak acid, the indicator, or the conjugate base of that indicator, the solution itself will experience a color change. Now we could write a generic equation showing the dissociation of this weak acid. I'm going to call the acid here HIN, noting again that it has a hydrogen cation present in it, and then the IN just stands for the rest of the indicator molecule. Upon dissociation of that weak acid, it'll separate apart into the hydrogen cation, H positive, and the IN negative indicator anion, that being the conjugate base of the species HIN. And again, recognizing that the species itself is a weak acid, I could write an equilibrium constant which governs its dissociation. That equilibrium constant Ka would be the concentration of the products over reactants, that is concentration of H positive, times the IN negative indicator anion, divided by the molecular species concentration of HIN. Now, to understand how this is going to work within a solution, let's consider the example problem here on our first slide. We're going to assume here that, again, phenolphthalein is an acid-base indicator which is used in those titrations. We're going to call the species HIN, the molecular species of this particular indicator. And the species IN negative is going to be the anion, the conjugate base. And as it turns out, the species HIN is colorless, and the conjugate base IN negative is magenta in solution. And our question is, what color will the solution likely turn upon addition of 0.10 molar sodium hydroxide solution to distilled water which contains a solution of phenolphthalein? And we want to justify your reasoning to understand this process. So, as a starting point, let's again begin with that dissociation equation describing the indicator HIN splitting apart into H positive and IN negative anions. If we consider that the NaOH solution is going to be a strongly basic solution, recall bases in solution accept protons, and that would imply, therefore, that the sodium hydroxide, OH negative, would accept hydrogen ions from the solution. And as such, those H positive ions formed from the dissociation of the indicator are likely to be essentially consumed by the hydroxide ions, and as such, the concentration of H positive in our solution should go down due to the presence of our hydroxide. And now let's consider this from a perspective of Le Chatelier's principle. If we see a decrease in the concentration of the H positive ion due to the presence of these excess hydroxide ions, that would imply that that H positive ion would collide less frequently with IN negative ions in solution, thereby decreasing the rate of our reverse reaction from the dissociation equation of the indicator. And as such, the net shift in equilibrium in this case should be a shift to the right. Now, having predicted a shift to the right by Le Chatelier's principle, recognize that from our givens in the problem, the species IN negative is described as the magenta species in solution, suggesting then that the shift right should cause the production of more IN negative, and therefore we would expect to see the phenolphthalein turn magenta in our solution. And that should correlate again to what we saw during our lab during last year, in which we saw the solution of the phenolphthalein turn bright magenta as the solution turned basic that we were titrating. So we've got a general idea about how this process works, and in terms of qualitative terms, over the next couple of slides, we'll now develop an understanding quantitatively how to understand when these color changes will take place. All right, for our next slide here, we're going to have a quick look at a quantitative understanding of some indicator behavior in solution. Suppose in example 2 that we give you again a generic indicator whose formula is HIN, and the Ka value of this weak acid HIN is given to us here as 1.0 times 10 to the negative 4. And we add some of that indicator to a solution. Now, the pH of the solution here is given to us as a pH of 5.00. We would like to ask you here, which is the dominant species present in our solution? The molecular species HIN or the conjugate base anion IN1 negative? And we want to justify our reasoning. So, as a starting point for explaining this idea, let's again go back to the idea that the indicator HIN itself is a weak acid in solution. And as such, we'll write its dissociation equation here, in which the species HIN will separate apart into the component ions of H positive and IN1 negative. And again, because this is a weak acid, we're going to write a K expression which governs its dissociation. That K would be a Ka, which in this case would be equal to the concentration of that hydrogen cation, H positive, times the anion I1 negative, all divided by the concentration of the molecular species HIN. Now, we've got our written Ka expression here. I'm going to do a quick manipulation of this expression here by simply dividing both sides of the equation by the concentration of H positive. And once we make this division here, my new expression now turns out to be the value of our equilibrium constant Ka divided by the concentration of the hydrogen cation H1 positive is now equal to the ratio of, on the right side here, the concentration of the indicator anion I1 negative divided by the molecular acid HIN. And this manipulation right here again shows me here a ratio of the conjugate base ion negative to the molecular acid HIN. So I'm going to go ahead now and solve for the value of that particular ratio by inserting the given values of the Ka and the hydrogen concentration that I can derive from the pH of this solution. So a given value here of my Ka was again 1.0 times 10 to the negative fourth. That'll go in my numerator. I'm going to divide that now by the concentration of hydrogen ion, which I can derive from the pH of my solution, which was given to me as a pH of 5.00. Recall the concentration of my hydrogen ion can be found by taking 10 to the minus pH, which in this case would be 10 to the minus 5.00, which yields a hydrogen ion concentration of 1.0 times 10 to the negative fifth molar. So I'll now insert that into my denominator of my rearranged equation here. And what I get now again is 1 times 10 to the negative fourth divided by 1 times 10 to the negative fifth, which yields here a value of 10. Essentially telling me here that the ratio of the concentration of the species IN negative divided by the concentration of HIN is a 10-to-1 ratio, implying therefore there is 10 times as much indicator anion, IN negative, as compared to the molecular acid HIN in our solution. So we can see here that the species which is dominant in solution is not only dependent upon the acidity of the solution, but also upon the Ka of the specific indicator which we are using. And that implies, therefore, the color change of an indicator will not always take place at a pH of 7, like we would like it to for a strong acid, strong base titration, but instead will take place at some particular pH which is dependent upon the actual Ka of the acid which we're dealing with. And therefore, if we're interested in selecting an appropriate indicator to use for a particular titration, it'll be useful for us to know the relationship that exists between the Ka of the indicator and the point at which the pH will be in an acid-base titration specific to the titration which we are performing. So we'll take a look at that on our next couple of slides. All right, now on this slide, we're going to have a look at the relationship that exists between an acid-base indicator and the Henderson-Hasselbalch equation, which we derived during earlier conversations in this unit as we discussed buffer solutions. Now, recall that the Henderson-Hasselbalch equation defines the pH of a solution as being the pKa of the weak acid plus the log of the ratio of the concentration of the conjugate base of that acid, which for our indicator would be the species IN negative, divided by the concentration of that molecular acid in solution, which would be for the indicator that we're dealing with, the species HIN. And as we saw on our previous slide, the relationship between the relative concentrations of the conjugate base IN negative and the molecular acid HIN is essentially a function of both the pH of the solution as well as the pKa of that indicator species. Now, as it turns out, for most people, the human eye is able to detect a difference in color if the ratio of the concentrations of the indicator anion, that is IN negative, versus the molecular indicator HIN, is a difference of concentration of around 10 to 1, or 1 to 10 either direction. Because the pH scale, again, is a logarithmic scale, what that really implies then is that you can detect a difference in the color of a solution generally as the pH of that solution changes by about 1 pH unit. Now again, remembering that our Hendelson and Hasselbalch equation tells me that the pH of that solution is equal to the pKa of the acid plus the log of the ratio of the concentration of ion negative over HIN. Remember, if those two species are equal in concentration, that is ion negative and HIN, that would mean that that ratio would be a ratio equivalent to 1. And if that ratio of the concentration of ion negative divided the concentration of HIN is equal to 1, then the log of that ratio would be equivalent to the log of 1, which is 0. And as such, the pH of the solution would therefore be equal to the pKa of the acid. So long story short, what that really means is the color change will be detectable by the human eye around plus or minus 1 pH unit around the pKa of the acid that you're using as your indicator. Now, the takeaway of that is that if you want to determine the endpoint of a titration, the indicator which you select in order to indicate where that endpoint occurs should have a pKa which coincides with where the endpoint of the titration lies in terms of the pH of the solution. Now, clearly for a strong acid, strong base titration, that pH would be around 7, which implies, therefore, the best indicator you could possibly use for a strong acid, strong base titration would have a pKa of very, very close to 7. Now, if you look on this pH indicator chart, you can see here that there's several indicators that undergo a color change right around that particular position. So if you have a look here real quick, you can see indicators like, say, bromothymol blue would be an excellent selection to use for determining the endpoint of a strong acid, strong base titration, as the color change of that particular indicator occurs between the pHs of around 6 on the low end up to around 7.6 on the high end, putting that endpoint of the titration right in the middle of where that color change would actually occur. Now, in some instances, however, the endpoint of the titration does not occur at a pH of 7. In particular, if you consider the titration of a weak acid, like let's say acetic acid, by a strong base, let's say sodium hydroxide. If you look at the reaction again that occurs as a weak acid is titrated by a strong base, the acetic acid, CH3CO2H, reacts to the hydroxide ion OH negative to form water as the first product, and then the second product again would be the acetate anion CH3CO2 negative. Remembering that at the endpoint there's equal moles of acid and base present, that implies that the major species present in solution at the endpoint of the titration is that acetate ion CH3CO2 negative, which itself is the conjugate base of a weak acid, and thus is a relatively strong base itself. And thus the endpoint of a weak acid strong base titration will occur at some pH which is above 7, because again, the presence of that relatively strong conjugate base. And as such, recognizing again that our endpoint will occur in the basic range of our solution, we might choose then to select a different indicator to indicate the endpoint of this particular titration. If you have a look down here, an indicator like maybe thymolphthalein would be a good choice, where the color change takes place at a pH range between, say, 9.3 and 10.5. So, to summarize here, if you want to select an appropriate indicator to define the endpoint of a titration, what you really want to compare is at what pH that endpoint will occur, and what is the possible range of pKa values of the indicators which you have available to use. You want as close as possible to have the endpoint of the titration's pH to be equivalent to the pKa of that particular acid you're using as your indicator, and as such, the color change will occur right around when the actual endpoint of your titration occurs. Now here's again a big chart which we've got a lot of different possible indicators that are present on here, and you see all of them have color changes that occur over different ranges because all of them are acids with various different Ka values. A couple of these, just interesting things to note, have two color changes that take place, like in particular if you have a look at the top here of thymol blue. Thymol blue undergoes a color change around a pH of 2 as well as around a pH of 8.5 or so. Now, a possible explanation for this observation would be that thymol blue, the indicator we're using here, potentially would be a diprotic acid. And correspondingly, as the diprotic acid would have two different pKa values corresponding to the loss of each of the two different protons from that acid. And with two different protons to be lost or gained during the course of a reaction, that also implies the possibility of two different color changes over the course of the range of pHs during the titration. So that's essentially how we're going to use an indicator in a qualitative sense here. Let's take a look at our next slide at a final quantitative calculation to make. All right, this final example problem that we're looking at right here is the type of problem you might be likely to find on, say, a multiple choice question on your AP test. This question is going to ask you to select the best indicator to use over the course of a titration of a particular species. Now, if you have a look at our graph we're giving you here, this titration here describes the titration of a weak base with a strong acid. And you see the shape of the titration curve that is now familiar to us here. We're starting off at a relatively high pH due to the presence of that base, and as we add more and more of that strong acid, that pH of the solution decreases until we reach an inflection point of that graph. And as you recall, that inflection point of that graph, where it changes from concave down to concave up, is where we see the endpoint of this titration. Now, that endpoint of the titration is occurring, it appears to me, at around a pH of somewhere close to 5 or so from the graphical picture which we're looking at here. So if the endpoint occurs at around a pH of 5, logically speaking then, that would imply that the visible color change would occur over a pH range plus or minus 1 pH value around that endpoint of our titration if we had selected the best indicator. So what I want to look at then is the list of available indicators they've given us here. We have as our options here phenolphthalein with a pKa of 9.3, bromothymol blue with a pKa of 7.2, methyl red with a pKa of 4.9, alizarin yellow whose pKa is 11, and then thymol blue whose pKa is 1.6. And clearly there is one indicator here which is a much better choice than all of the others. Again, because the endpoint of my titration is happening in the acidic range here due to the presence of the conjugate acid which is formed over the course of the reaction between our weak base and strong acid. That implies, therefore, that I want to select the indicator whose pKa most closely aligns to the pH at the endpoint of the titration. And clearly, because at the endpoint it appears that the pH there is 5, that would imply, therefore, that the indicator methyl red, whose pKa value is 4.9, would by far be the best choice of our options. And to contrast that with some bad choices, have a look at what we would have had occur had we used the indicator alizarin yellow as our indicator. Alizarin yellow, as it turns out, has a pKa value of around 11, which implies, therefore, the color change will happen over a range of somewhere between around 11 plus or minus 1 pH units, which would be between around 11 to 10 as we go down. And that implies, therefore, if you have a look at our titration curve, that that indicator will already be approaching its color change or even already engaged in a color change as the very start of the titration occurs. Now, in the opposite direction, if we had chosen the indicator thymol blue, whose pKa is around 1.6, that would imply again that the color change for this indicator would occur around plus or minus 1 pH units around 1.6, which would be on a range between about 2.6 down to 0.6. And if you have a look there, at a pH of 2.6, we are well past the endpoint of our titration, implying, therefore, if we used that species, that is thymol blue, as our acid-base indicator, we would already have well crossed the endpoint of the titration by the time we start to observe the color change taking place. So again, best case scenario here, select the indicator whose pKa is closest to the pH of your solution at the endpoint, and that will give you the color change which most closely aligns with the endpoint of the titration occurring. All right, so though there may be some more quantitative calculations you'll come across as you look at the assigned book problems relating to acid-base indicators, for the most recent version of the AP test, they have really heavily focused on the qualitative application of this concept. And really, for the most part, all you have to be able to do in the most recent versions of the test is to select an appropriate indicator to find that endpoint of your titration. So you're certainly welcome to explore those more quantitative aspects, but in recent years, a more qualitative understanding of this concept has been sufficient for success on that AP test. All right, and with that, we now conclude our discussions around aqueous solution equilibria in Chapter 15. Thank you so much for listening, and we'll see you at the next lecture.